Okay folks, we're going to start Unit 3, which is going to look at some applications and extensions of derivatives. Since y'all are getting pretty good at taking derivatives, it'd be nice to figure out what we actually do with them. One of our first applications is to take a look at equations of tangent lines. So we're going to talk about how we find equations of tangent lines and also what they look like graphically. The first thing for you to note is that you've talked about lines for a long time in the past. In fact, you've learned several different equations for lines. One of those is standard form. And standard form is one of those ones where you have some coefficient in front of your x plus another number in front of y, and usually we set it equal to a constant. Standard form is not a form that we typically use in calculus. In fact, standard form is not a form that most people use at all. But there are a couple of more useful forms. One of them is this form, y equals mx plus b, the super familiar y-intercept form. And then another form that we're going to talk about is slope-intercept form. Now, slope-intercept form is a form that you've probably talked about before, but it might not be as familiar. It might not be your go-to. Slope-intercept form has a y on one side. We're going to subtract off some number, which is a y1. That's going to be equal to the slope m times x minus some other number, x1. Now, it turns out in calculus, we can have a choice between using either the y-intercept form or slope-intercept form, but for our purposes, because we are mathematicians, therefore lazy, I will focus on using slope-intercept form. This will save us a lot of time. It'll keep us from having to solve for the y-intercept. And so as we do these problems, I want you to keep in mind that we are wanting to get very familiar with slope-intercept form of a line. So let's take a look at an example together. You might come across a question like this that gives you an equation, such as y equals x squared plus 4, and then it's going to ask you to find the equation of the line tangent at x equals 3. Now, we're pretty savvy folks. We know that x squared plus 4 is the graph of a parabola. I'm going to sketch it over here. Since we have a plus 4 right here, that means my parabola is moved up 4. So I'm going to move up 4. Put that, and I'm just going to draw a very general parabola shape. This problem is asking us to find the equation of the line tangent to the curve at x equals 3. So I'm going to go out to 3 on my x-axis, 1, 2, 3, and I'm going to go up and put a dot on my curve. Now, we've done things before where we sketch tangent lines, and that's what I'm going to do now. So we're going to sketch the tangent line. And essentially, what we're going to be doing in this problem is finding the equation for that tangent line. Now, to get us started, we're going to use our favorite point-slope form, which is y minus y1 equals m, x minus x1. The x1 and the y1 are an xy pair, and it's any point on the curve at all. And so we just have to find a point on that pink curve. We'll substitute that in for x1 over here and y1 right here. The other thing that we're going to need to find is the y-intercept, and the other thing that we're going to need to find is the slope, which is right here. And one of the things that we've learned in calculus is that slope is code for slope of the tangent just means derivative, which is going to give us our m. So to get us started, let's go ahead and take the derivative of our original function up here. So we're going to grab this function, we're going to use our derivative rules and find the derivative. So y prime equals, this is a pretty easy power rule problem. We've got 2x. The derivative of this 4 right here is going to be 0. So here's my y prime. Y prime equals 2x. Now, if we want to find the slope at 3, let's evaluate y prime of 3. I'm going to replace that x with a 3. I end up with 2 times 3, which is 6. And that 6 right here is my m. I'm going to put it in my equation in just a second. Over here we'll put a box for our answer. And we'll fill in the pieces as we go. The y for my slope-intercept form is going to stay y, minus, we're going to fill in a number right here in just a second, equals this 6, that's my slope, goes right here. And then we're going to have x, which stays x, minus, and then a number. Now to figure out our xy pair, matters aren't too terrible. In fact, the problem has already told us the x. They said we're interested in x equals 3. So that means my x1 of my xy pair is 3. I'm going to sub that in over here for my x1. Now we're pretty smart cookies. We know that if we have the equation y equals x squared plus 4, and we need to find the y coordinate, we're just going to take 3, sub it in for the x. So 3 squared is 9, plus 4 is 13, I think. So this is my x1, this is my y1. I'm going to substitute my 13 over here for my y1, and now I'm done. No simplifying, no need to distribute that 6, life is good. There's the equation of our tangent line. What we'd like to do next is talk about something related to tangent lines. It's something known as a normal line. Okay, and a normal line and a tangent line are super similar. The only difference is that they're perpendicular. So, it's worth jotting down that normal is actually just another word for perpendicular. And I'm going to re-sketch the drawing from a second ago. You have it on your notes already. We had a parabola like this. It was up at 4. A moment ago we found the tangent line at 3. That's this guy. If someone asked you to find the normal line, the equation for the normal line at 3, then you'd be finding the equation of the guy who was exactly perpendicular to the blue tangent line at 3. Okay, so we have an equation of that orange line. And luckily for us, solving for that equation is pretty straightforward. We'll do an example together next. Let's check out this one. Example 2 asks us to find the equation of the normal line to the curve f of x equals 2x cubed at the point x equals -1. Now, since we're finding the equation of a line, a normal line, we know that we're going to use our point-slope form, y minus y1 equals m times x minus x1. I'm going to smile to myself because I already see my x1 value. It's right here. Okay, in a moment we can use that to find y1. But I think first I'm going to find the slope. And we need to start out with the slope of the tangent line. The slope of the tangent is what we find with our derivative. And then we're going to use the slope of this tangent to find the slope of the normal up here. Now we know that slope of tangent is code for derivative, so let's find f prime of x. It's another pretty straightforward power rule. I've got 6x squareds. I want to find f prime of x when x is equal to -1. So I want to take this x right here, I want to replace it with a -1. So that's going to give me 6 times -1 squared, which is just 6. Now we have to be careful because this right here is the slope of tangent. We need the slope of the normal. And we're pretty lucky because tangents and normals are perpendicular. And one of the things y'all learned is that if you have a tangent line, if you have a line that's perpendicular to it, then their slopes are going to be opposite reciprocals. So we need to take this 6 and we're going to change it. We're going to invert it, make a reciprocal. There's 1/6, and we need to have the opposite sign, so negative. And it turns out that this -1/6 is the slope of our normal. I can put that in place for m. -1/6. I'm going to go ahead and substitute my x1 in. X minus, and then we have minus and negative, so it changes it to a positive 1. Okay. The last step is to go ahead and find my y1, and in order to do that we just need to find the original function f up here, this guy. We need to evaluate him at -1. So let's just replace that x with a -1. We're going to cube it, and that should give us negative 2. Now that we have y1, we can replace this negative 2 up here, and there's our equation of the normal. Next on our list, we have one tiny thing left to do. It turns out that there's also something in this section called higher order derivatives. And what we've been finding, we've been calling it f prime of x. That's technically called the first derivative. And where there's a first, there's bound to be seconds and thirds and fourths and so on. And so we want to be champions at finding higher order derivatives. The first thing you need to be aware of is that there's some notation. So we've been finding f prime of x. That means first derivative. If I wanted to notate the second derivative, then what we do is just add another prime in place. So f double prime of x means second derivative. I could have the third derivative, f triple prime of x. Now, y'all, at some point, math folks get really bored of writing all of these primes, and so you might see, for example, at fourth derivative, they're too lazy to write 4 primes, so they put a little 4 in parentheses up there. That just means fourth derivative. Now we know that there's other notation for derivatives, so another notation we've seen is dy dx, this fraction notation. If somebody wanted to use that blue notation for second derivative, they would write d and a little squared y over dx squared. And similarly for third derivative, d cubed y over dx cubed. Those are the most common examples of notation for higher order derivatives. Let's take a look now at a question that you might come across in the future. Here's an example, example 1. This problem asks us to find f double prime of x. F double prime of x is the second derivative. ATIV. And it's asking me if f of x is equal to 5 over x to the fourth. Now in order to find the second derivative, we're necessarily going to have to find the first derivative. So let's find f prime of x first. I'm going to go over to my original problem. I'm going to change a little bit about how it's notated, how it's written. So this guy's a fraction. He's 5 over x to the fourth. There's a couple of ways you can solve this. This looks like a quotient rule sort of situation. So one way you can solve it is a quotient rule. So I think I'll do it that way. I know that my first derivative over here is going to have me do low d high. So I've got x to the fourth times the derivative of high. The derivative of any constant by itself is 0, minus high d low, 5 times 4x cubed, over low low, x to the fourth, all squared. Now we know that AP doesn't force us to simplify anything, so we could stop right here at this red answer. However, if I'm going to find a second derivative, usually it's in our best interest to simplify a little bit. So I'm going to go out to the side over here. I'm going to simplify this just because it's not so terrible. This whole section goes to 0. I end up with negative 20 x cubed over x to the 8th. Remember, if you have an exponent to an exponent, you multiply. In fact, I can do a little better. I think I will cancel out some of those x's, so I have 20 over x to the 5th. And the reason I would choose to take the time to simplify that is because now, when I take the derivative of the derivative, I get my second derivative. So the second derivative happens when you take the derivative of the first derivative. So let's do that. Let's go ahead and use our quotient rule again on this problem in order to find the second derivative. Here we go. So I'm going to use quotient rule again. I've got my low d high, x to the 5th, times the derivative of this negative 20 is 0, minus high d low, 5x to the 4th, over low low, x to the 5th, all squared. Now, since I don't have to go any further, and I'm a mathematician, so I'm lazy, I'm going to stop right here. If you wanted to, you could totally simplify that. It wouldn't be wrong, just don't mess up. But since I don't have to find a third derivative, it just takes less time to go ahead and stop right there. So that wraps up the first of our sections of applications of derivatives. So be sure to keep these notes handy, make sure you've copied everything down, and you can use them for reference.